So we have looked at the laser beam welding process. To summarize what you have done so far in the laser beam welding. So we looked at type of laser sources, so various sources in solid state and gas as well as in fiber modes. We looked at it, and then we looked at the typical welding laser welding setup. So the modes of welding. So what is keyhole welding? What is conduction mode welding? What is the importance of keyhole and the reasons why we should have a stable keyhole in order to have a good aesthetic weld as well as spatter free weld. And we will have to look at the various forces that are actually affecting the keyhole stability. Right. So we looked at the effect of vapor pressure in overlap joints. We saw some examples with galvanized steel with varying thicknesses of galvanized layer, how the vaporization of the zinc affect the keyhole stability in laser beam welding. And then we looked at various welding parameters that generally we use for laser beam welding processes. So as I already explained in automotive welding industries, resistance spot welding and laser beam welding are most commonly used welding processes. And apart from these two processes, still the gas metal arc welding, the conventional GMAW is also used for very specific applications. So it is also good to look at the principles of gas metal arc welding, especially we have made some advances in gas metal arc welding processes. Conventional process we use in a constant current. For example, the amplitude of current is constant throughout the welding process. There are some disadvantages in terms of heat input, the amount of heat you put it in the workpiece, as well as the transfer characteristic. So what do you mean by transfer characteristic? Now how you transfer the molten droplets from the electrode to the workpiece. So in order to improve the transfer characteristic to our benefit, as well as to reduce the heat input, and we modified GMAW, gas metal arc welding, and then these modified GMAWs are sometimes used in automotive industry to weld thicker sections. For example, thick section advanced section steels or even high section steels that are used, or in some applications where the material, the weld strength is not really significant. So we may also use the GMAW processes to do a brace joint, do bracing. It is different than the conventional GMAW, the welding process, and we were used low melting fillers to make joints of advanced section steels. So in order to understand all the welding processes, I will also like to give you an overview of GMAW, because in subsequent classes we will also be looking at GMAW bracing process as well, which actually is very useful to join advanced section steel in some of the body parts. Okay, so we will move on to the GMAW process, gas metal arc welding process, and most of you are familiar with the schematic of GMAW. See, this is one of the oldest processes, welding processes. It developed to weld conventional materials. So there are three important parts you can see here. The first important, foremost important is the shielding gas, and shielding gas is also known as arcing gas because we strike an arc using this shielding gas. And the filler wire. So in this case, the filler wire is a consumable electrode. So it's called consumable because we melt and consume the electrode to fill the weld cavity. And the third important aspect in terms of process is arc. Okay, so arc is struck between the consumable electrode and the workpiece using the shielding gas. So I don't want to go into detail about the physics of arc, which I'll be covering in subsequent NPTEL courses, the physics of arc. So right now we can assume that so the arc is struck between the consumable electrode and the base plate by passing a current over the potential difference voltage generated across the circuit. So current is passed through the electrode towards the workpiece, and then because of the ionization of the shielding gas, we produce the electrons and ions, and then we strike an arc between the electrode as well with the workpiece. And the various the components of a typical GMAW process is also shown over here, and we have a gas nozzle and a contact tip, and contact tip actually feeds the electrode towards the workpiece. The electrode is a filler wire, it is consumable, and this can be either similar or dissimilar consumable based on the various welding metallurgy principle microstructure what you want to generate, and then upon passing a current you form an molten droplet of the tip of the electrode, which is transferred by various means towards the workpiece. So we will see in detail what are the process parameters that can significantly affect the welding process, as well as the stability of the weld in subsequent slides. So right now we can assume that in a gas metal arc welding process, so we use a shielding gas to strike an arc between the consumable electrode and the workpiece. The gas is ionized and forming electrons and ions, and based on your polarity, and they can travel either from electrode to workpiece or from workpiece to electrode, and the entire the heat is generated by passing an amperage towards the setup from a power source, and the setup is maintained to a potential difference of volt V. So I will show you in a small video about how the GMAW, the gas metal arc welding in action, so it will be better clear for you. So this video shows the consumable electrode, the gas metal arc welding process in tandem. So we have two electrodes attached to a power source and transferring a molten droplet towards the weld pool. So what you see over here, this is one filler wire and another filler wire, and we are passing varying amount of currents based on the current, and we may either transfer droplets in a spray mode, or in this case as a globules in a rippled mode. So the characteristic of metal transfer is very critical, as we explained in laser welding, and how the keyhole is important for stability. In this case, the transfer characteristic of the droplet is extremely important, and you can already see here, we have the molten droplets are sprayed towards the workpiece, and whereas in the other electrode, the droplet transfer is mostly by globules of a molten electrode droplet, and because of the change in transfer mode, and this mode would also tend to spend a lot of spatter towards the other direction than the workpiece direction, forming spattering. So the important characteristics of this process are controlled by the current, the amperage we send, the sealing gas what we use, as well as the melting characteristic of the electrode, which is also controlled by the current, as well as the diameter and the stick out length, the distance between the contact tip to the workplace. The other aspects of GMAW which you to see, so again the schematic is shown in this slide. So this can be seen to understand the entire the transfer characteristics and the cross section of the weld pool what we generate. So we have the consumable electrode, and the electrode and the workpiece is connected to a power source, and this power source transfers the current. It can be either alternating current or direct current. And so if it is alternating current, we use a transformer. If it is direct current, it is an inverter based power source, and this the power source is sending an amperage towards the welding electrode and the workpiece, and the electrode can be either positively connected or negatively connected, and if you have a DC source, this can be electrode positive or electrode negative, and based on the polarity you also change the heat transfer characteristics. So I don't want to go in detail about the physics, but you can assume that when it is an electrode positive, and then the filler becomes an anode, and if it is electrode negative, your filler becomes a cathode. And if it is electrode positive, so you would be sending ions towards the workpiece, and the electrons will be attracted towards the filler. If it is electrode negative, okay, so you will be attracting the ions towards your the electrode, and you will be transferring the electrons towards the workpiece. Based on your current characteristics, you will also change the droplet shape. As already explained, when you have a current low current mode, you will be transferring the droplets in globular mode, and by increasing current, the diameter of the droplet which is transferred from the workpiece decreases, and you will end up transferring in spray mode from the electrode tip to the workpiece. And if you look at the actual characteristic of the arc welding process, so we use the consumable electrodes. Generally the distance between the electrode workpiece, sometimes it is also known as CTWD. So it is contact tip to workplace distance. So contact tip is the electrode container which actually transfers the electrode towards the workpiece, and the distance between the contact tip and the workpiece is very critical, because that is going to determine the stick out length, and the stick out length is one of the important parameters which determines the melting rate of the electrode. And we can either use an alternating current or direct current, and based on our need. Generally we can choose between the direct current, alternating current. For example, welding of aluminum is generally done in alternating current, and use of DC is preferred in welding of steels, because we can also manipulate the waveforms very easily within a direct current. Either you can do it in a pulse current, or you can also do it in with various modes of the waveforms. So waveforms, by meaning waveforms, what we mean is the variation in the voltage and current in a given welding cycle. So welding can be done either with a single pass. So if you have a very thin sheets that are going to be welded, you can also weld it within a single pass, or if you have a thick sections, welding is also carried out in multi passes by sequentially placing each pass on top of each other. Generally in welding of automotive steels, if you are doing using a GMAW, and most of the cases we will be doing a single pass, and some cases we may also have to do in overlap configuration. So we will also be doing it in overlap configuration, like in a lap joint in a fillet mode. So we will be doing welding in overlap configuration. This is the most preferred mode of welding, especially if you are doing an GMAW bracing. So in this case, the bracing is done using a low melting filler, where say for example in advanced size steels, so we use a copper based fillers, CuSA3 or CuAl7, the copper based fillers, and we melt and deposit the fillers to join to overlapping advanced size steels by carrying out a fillet weld. So in this GMAW, the heat input is determined by a very simple equation. So where we have the voltage and current, which is actually passed to the current is passed to the system over a voltage V. So the heat input which is calculated in joules per mm, which is actually nothing but the NP, which is the process efficiency. Process efficiency determines how much heat which is generated in arc is transferred to the workpiece, times the voltage of the circuit, and I the amperage, the current you send it into the system, and here the V, the speed of welding. So the important parameters here is the efficiency. The efficiency of the process is determined by the various factors, including polarity of the source. Either you keep the electrode positive or negative, and your shielding gas characteristics, as well as the process characteristics, such as whether your arc is completely shielded or arc is completely protected from atmosphere, whether all the heat that is generated in the arc is transferred to the workpiece or not. So generally the NP can be calculated for a given composition of the filler wire and the configuration of the process. Generally the NP is calculated based on the polarity. For example, if you look at a typical GMAW setup, we have 3 regions in the GMAW schematic. If you look at it, and if your electrode is positive, and you have the anode, which is your filler wire, and you create an anode fault zone and an arc column surrounding the anode, and if your electrode is positive, obviously workpiece is negative, then you have a cathode fault zone just above your workpiece. So these 3 distinctive regions is always present in GMAW. So in this case, if you look at the voltage distribution, and you have a more or less constant voltage along in the arc column, and because of accumulation of electrons in the anode fault zone, and because of the accumulation of ions, positive ions in the cathode, you have a steep voltage gradient in these 2 regions. And based on your polarity, you may either transfer the electrons from the filler wire to the workpiece. In this case, you will be transferring ions towards the workpiece, and if your the workpiece is negative, obviously you will be transferring electrons to the filler wire. So based on the polarity, you will be transferring the electrons and ions, but in a GMAW process, you will also be melting the electrodes, and you will be transferring the droplets as well to the workpiece. So then the efficiency can be calculated very easily. Is so process efficiency is nothing but the total arc energy that is transferred to the workpiece, right? So in this consumable electronic process, so you also melt the consumable and then transfer the droplet to the workpiece. So the total efficiency is the amount of heat generated in the cathode as well cathode fault zone plus the heat generated in the anode fault zone, and because we are transferring the droplets from the electrode to the workpiece, the total heat generated is QC plus QA, and so that the total heat transferred and over the amount of the energy supplied to the system, there is nothing but Vi and times 100, that gives you the efficiency of the process. So in the conventional GMAW process, the energy efficiency it's not that significant, but it is much more than the laser welding process, because the laser welding process we already looked at the absorption of laser to the workpiece is extremely small. So whereas in this case the heat transfer from the arc is entirely determined by the atmosphere as well as the polarity. So as I explained, whether you have a filler as an anode or cathode, irrelevant, because you will be transferring, you are melting the filler, and you will be transferring the entire heat that is there in your electrode towards the workpiece. So if you have a non-consumable welding process, for example, if you have a gas tungsten arc welding process, there you are not transferring the entire heat from the electrode because you are not melting the electrode, right? So then based on your polarity, it can be either QC or QA. So that will be your efficiency of the gas tungsten arc welding process. So that's why generally in gas tungsten arc welding process, the efficiency is quite low, whereas in a GMAW welding process, you can have the efficiency of the process going up to 60 to 90%, and based on the heat transfer from the arc to the workpiece. And you also see I listed various processes. The other variant of GMAW is the submerged arc welding process, which has an highest efficiency. Why? Because the arc envelope is completely covered by the flux in a submerged arc welding process. So whatever heat that is generated is entirely transferred towards the workpiece. So that determines the efficiency of the process. So for a GMAW process, we can see that the efficiency, the amount of heat that is actually transferred from the arc to the workpiece is somewhere between 60 to 90%. So we can calculate the heat input from the efficiency. For example, if you assume say 0.6%, then you can use a voltage, and that can be instantaneous voltage or the mean voltage. and then the current over the velocity, and that will give you the amount of heat that is generated in joules per mm. Okay. So the other important parameters in consumable welding process is the melting rate of consumable. So that is also very important to understand, because that determines your weld bit geometry and your productivity. So that is again, it's a function of the amount of heat that is transferred to the electrode, whether we are going to keep the electrode as a positive or negative. So in this case, so if your electrode is an anode, so you will have the amount of heat that is there in your electrode tip, and the filler material parameter, the energy needed to heat up the electrode towards the above melting point, and these two together you would have an equation ultimately will leading to the melting point of an electrode, which is nothing but a constant, and this constant is a function of the parameters which controls the characteristic of GMAW process. For example, the anode voltage, anode voltage, the voltage at the arc column, and your the cathode ionization potential, and then the amount of heat needed to heat the your anode so to the excitation temperature or ionization temperature, and over the heat required to melt the electrode and hit the electrode tip above your the melting point. So with that now we can calculate the melting rate. So it's nothing but the constant over current. The current is your the welding current, plus the another constant which is a function of material, and then L is the stick out length. The stick out length is nothing but the distance between the contact tip to the workpiece, so which we already explained in the previous slide. And the stick out length is very important because that determines your the resistance heating part of the electrode, and then again I is the welding current, and pi as well as the it is an universal constant, and then R is the your the diameter radius of your filler wire or electrode. So using this, so the A and B is a constant for a given material and for a given process conditions, whether it is electropositive or negative. So if you know A and B for a given stick out length and your filler wire diameter, we can calculate the melting rate for a given welding current. So I have given some of the constants A and B is used for commonly common welding wires. For example, if you have 1.2 millimeter plain carbon steel as a filler, so we can get an A and B calculated from the experiments. It says for example A vary from 0.3 and then B is 5 in 10 power minus 5. And using this value, if you know the stick out length, the L as well as your welding current and your radius. So in this case the diameter is 1.2 mm diameter, so it will be 0.6. So using that you can calculate the melting rate of the filler for a given current I. So obviously if you look at these equations, and if you have longer R, the bigger R diameter is increasing, then your melting rate decreases obviously, and if your stick out length increases, you will also melt more. And of course if you have a higher current, you will also melt more. So the main important parameters for a given composition and given wire diameter, that means if you fix R as well as if you fix in A and B, the important parameters you can vary to change the melting rate is the stick out length L and the welding current. Right. So it's very important to understand the important factors that can influence your melting rate for a given diameter of the wire as well as for a given process condition. That means that if you use electrode positive and if you fix the other process parameters, for example shielding gas, the important factors that can influence your melting rate is the stick out length and the welding current. So this graph this shows the effect of the stick out length on the burn rate or the melting rate of 1.2 mm plain carbon steel in argon plus 5% CO2 atmosphere. As already explained, we fix the diameter, your shielding gas is fixed, and in this case these experiments were carried out in electrode positive conditions if you look at the reference book. So with that conditions, if you change the stick out length, so if you increase the stick out length, what happens? Your melting rate also increases. So for example, if you have a 20 mm stick out length and 10 mm and 5 mm for a given base current, given welding current, so you would end up melting more, and if you have a longer stick out length. So whereas if you have stick out length of 5 mm compared to 20 mm for a given current, you will be melting less than when you have a stick out length of 20 mm. Similarly, your wire diameter also changes your melting rate. As already explained, if you increase the wire diameter, so obviously your melting rate decreases. So if you want to keep your arc length constant, so you always have to have a wire feed rate also equal to your melting rate. So in order to keep the arc length, the length between the tip of the electrode towards and the base metal, if you want to keep the arc length constant, so you may have to feed the wire at the same rate you are melting. Okay, so the when you want to keep the arc length constant, so obviously your wire feed rate should be equal to the melting rate, and so once you have a constant arc length, so your wire feed rate equals your melting rate, and then as a function of wire diameter, you keep the stick out length constant, and if you change the wire diameter, obviously by increasing diameter you are melting less. So in this case, if you have the mean current of 200 amperes of welding current for a constant stick out length and for a given shielding gas, so for larger diameter wire melts less than the smaller diameter wire. So obviously if you reduce the diameter, your melting rate increases for a given welding current. So it is very important to understand the basic physics. I won't go into detail about the why the melting rate changes with function of current and the derivation of the equations of the melting rate as well as the efficiency, because I will be covering in detail in my subsequent MOOC class of welding processes. So right now you have two equations I showed you which are very important. How to calculate the heat input. Heat input is nothing but the efficiency times voltage current divided by welding speed, and the efficiency we calculate based on the polarity and for a given the shielding gas and the arc envelope transfer characteristics, we can calculate the heating rate. Generally the efficiency for GMAW, it is calculated by an average of the current in cathode and anode. So we can assume that the total heat is generated in anode and cathode is transferred to the workpiece, and then we can calculate the heat in the efficiency of the process as I had explained in the equations, and that is coming around 60 to 90% the efficiency process. Generally we assume lower efficiency 60% to calculate the heat input of GMAW process. So once you know the efficiency, we can also calculate heat input, and the heat input can be used to understand the thermal cycles of GMAW process. So the other important factors is the melting rate of the equation, the filler wire, and that is actually calculated as a function of welding current, stick out length, and wire diameter. So if you increase the welding current, obviously you melt more and your melting rate increases. And if you increase the stick out length, again the resistance heating also increases, thereby melting rate also increases. And if you reduce the filler diameter, you also melt more, and if welding and diameter increases, your melting rate also decreases. So with that we'll move on to the metal transfer characteristic of the droplets. Yeah, thank you.